to the second lesson on counting. If you've just joined this video, you might want to look at part 1, otherwise you're going to be spending a fair bit of time thinking, why on earth is a GCSE and A-level maths teacher teaching us how to count? We're actually looking at what are known as combinations and permutations, which refers to a puzzle that I put out a few weeks ago, or a few days ago, depending on when you're watching this, or even a few minutes ago, if you're watching in sequence. We're looking at counting and different ways of doing it to make larger objects easier to deal with. The recap is that we had to choose from 3 boys and 2 girls, and we needed to figure out a nice quick way of figuring out how many different combinations there are if we couldn't list them. In this case, it's very easy. We had A and D, A and E, B and D, B and E, C and D, C and E. Nice and easy. But what if those numbers are bigger? Let's say I have got 5 choices for a starter course, 4 choices for main, and 3 choices for pudding. Now, this is used in advertising all of the time. Literally thousands of different combinations, loads of games that say you could have umpteen different unique sets of armour. Do they actually mean thousands and thousands and thousands of different sets of armour, or do they mean you can choose from these different kits and you can kit out your character in a certain way? So, say for instance, here with the starter task, if I've got 5 choices for a starter, 4 choices for the main and 3 for pudding, how many different meal selections are there? Now you might be tempted to write them down as, say, 5 different starters, 4 different mains, 3 different puddings, and then counting up all your different combinations. Trust me when I tell you, that is going to take you a long time. So is there an easier way of doing it? Yes, there is. If I had 5 starters and 4 mains. Let's forget about the pudding for now. 5 starters and 4 mains. For each of those 5 starters, I've got 4 different options that come afterwards. So your brain should be jumping to 5 times 4. Because 1, 2, 3, 4, 5, 4, 4, 4, 4 and 4. That's 20 different options to begin with. 20 different combinations of a starter and a main. Can we extend that to pudding? Yes, of course we can. For each of those 20 options, I can then tier off and have 3 different desserts. Now that's the original 20 options multiplied by 3 to give us 60 different unique options. For each move in a path, I can move north, south, east or west. Perfect. 4 of those. I make 3 moves. How many possible paths are there? That would be 4 times 4 times 4. Oh. Weren't expecting that, were you? Probably in your head thinking 4 times 3, that gives us 12. Let's look at how we get that. I can move north, south, east or west. That's 4 different directions I can take. In my next set, what am I going to multiply that? You can think about this as, say, now the main course. We've had the starter direction. For the main course, how many options do I have? I still have 4. I can still move north, south, east or west. Forget about the fact that some of these are redundant. If I move north then south, I get back to where I started. We're not worried about that. We're thinking about the different commands, the different directions that we could go in. So to begin with, I've got 4 choices. In my second phase, my second move, I've still got 4 choices. Then in my third phase, in my third move, I've still got 4 choices. 4 times 4 times 4, 64 unique paths. This is where it starts to get interesting. So again, as a little pause, I'm going to let you have a go at that for yourself. Thankfully, the board isn't covered by my face, so think of them as choices, have a go at them. I'm just going to assume that you've paused and keep talking. So question number 1, the number of possible letter, quote-unquote, words where the letters are unrestricted. What does that mean? It means what combination of 2 letters. You pick 2 letters, could be randomly, could be whatever. How many different options do you have? Well, in the first case, there are assuming there are 26 letters in your alphabet, you've got 26 choices. Your second letter, you've still got 26 choices. So, that's 676 unique combinations. The number of possible 3-letter words where letters are unrestricted. Surely that's again 26 times 26 times 26. It is indeed 26 cubed, or 17,576. Now you might be thinking that's a heck of a lot, and if you're thinking, does password protection get involved in this? You'd be absolutely right. Loads of different combinations. That seems a lot, but bear in mind the speed that a computer can go through password checking if somebody wants to hack in is phenomenal. So 17,576 isn't a massive amount. So let's look at number 3. The number of possible 2-letter words where the letters are different. So how can we be systematic about this? Let's assume that we want to choose the first letter, which is 26. We've lost one of the letters now. Assuming I've chosen my first letter, I can't repeat that. The letters have got to be different, as is stated. Now we've got 26 times 25 different options, which is 650. Question number 4. Number of 4-letter words where each letter cannot be the same as the previous letter, but is otherwise unrestricted. I think that's a lovely one. That's pretty tricky to wrap your head around. Until you think about what's going on, do it sequentially. First letter, 26 options. Nice and easy. The next letter cannot be the same as the previous, so we've only got 25 options. The next letter could have the first, so we could start with L-O and go back to L, oddly enough, but we still can't go back to the second letter. So we still have 25 options. What about the fourth letter? Let's assume I've gone with L-O-L. Can I have another L as the final one? No. Could I have the O that came beforehand? Yes, of course I could. So actually, this is going to be 26 times 25 times 25 times 25. Because of that one simple rule. Now you could just write 26 times 25 cubed. That'd be absolutely fine. You'd get the full marks for that. Because that is in fact the answer. Your calculator will give you a numerical value, but you can see already by 4 letters, the numbers are already blowing up in a way that is going to become very hard to identify with up here. Now let's look at question number 5, because we've actually been given some pretty serious restrictions. The number of 4-letter words, each using A, B, C and D exactly once. So I can only use 1A, 1B, 1C and 1D, but they can be in any order that I want. Anyone who watched the puzzle that I gave out last time will be starting to cotton on here. The first section, the first letter that I pick from these 4, I've got 4 choices. But after I've picked, I'm down 1. I've only got 1 left, so I've then got 3 choices. After I've picked my second one, I only have 2 choices, followed by 1 choice. 4 times 3 times 2 times 1. Again, the eagle-eyed of you will remember the fancy word that I coined in, which is factorial, and factorials will come in later. Let's have a look again at the number of 5-letter words using the letters A, B, C and D exactly once. Now we can treat the 2 A's as being something different here, so that's where things get a little bit fun. Because you'd be tempted to come up with loads of different combinations here. Here's an elegant trick. Let's call the first A A1 and the second A2. So we've got A1, A2, B, C and D. We can employ the same trick we did in question 5. We can say 5, 4, 3, 2 and 1. That's great, that's lovely. But let's just say that I started with A1, A2, B, C and D. What if I'd also got the combination A2, A1, B, C and D? Would those copies appear absolutely everywhere? Yes, they would. So what do? We simply divide by 2. Because we could swap the A's literally anywhere where they would have appeared, and we'd get the same quote-unquote word. So we just divide by 2, and that tells us that we have 60 unique combinations with those 5 letters. Let's say that the restaurant serves 9 dishes, Amir and Ben both choose dish. How many different ways of choosing are there? Well, that seems fairly trivial, surely. 9 times 9. Amir has got 9 options, Ben's got 9 options. It is as clear-cut as that. A restaurant serves 9 dishes, Amir and Ben both choose a different dish. How many ways of choosing? Actually, it's not that bad either. If we assume that Amir chooses first, we can say that there are 9 possible options for him. All we know is that if Ben has a different dish, there's only 8 things he could have had. What's really pretty about this, I think, is that it is perfectly symmetrical. Some of you might be at home grumbling, going, well, why not let Ben choose first? Well, let's let Ben choose first. He has 9 options, then Amir has 8. 72 options altogether. It's as easy and as symmetrical as that. I want a football team of 2 people, just a goalie and a striker. 5 people to choose from. How many possibilities are there? So this is where we're going to look at the difference between order and non-order. Why is that? Because to begin with, in a similar vein that we saw with choosing the menus, we've got 5 choices for the goalie, 4 choices for the striker. Easy. What if I said, I want a football team of 2 people, and I've got 5 people to choose from? So I'm not going to assign them goalie and striker. I'm just going to chuck them onto the pitch and say, there you go. Now that they're choosing doesn't matter, now that their list doesn't matter, it doesn't matter which way I've ordered them. Suddenly, there's an issue. Let's say I've got Chloe and Connor on my football team. Before, I had 5 choices and I happened to have chosen Connor. Then Isa happens to have chosen Chloe and she became the striker. Now, they're just the players. So, all of those possible different combinations before, where I selected them and said, you're goalie, you're striker, what if I got it the wrong way round? What if, to begin with, I'd chosen Connor as goalie, then Chloe as striker? Somewhere down that list, I've chosen Chloe as goalie and Connor as striker. Actually, all those now merge, so we need to divide by 2. And you can see this graph, this visual representation here, which is really quite beautiful, showing you that actually the first question is symmetrical to the second. We've just got to think about whether or not order matters. In the first question, order does matter, so there are more options. In the second, we half it because order doesn't matter. So here's our exam-style question. And you can see already the numbers have gotten a lot bigger, which is why we just want some fraction or multiplication to show us the number of pairs. 17 men, 26 women in a choir. They're singing at a concert. We're not bothered about a concert. One of the men and one of the women are going to be chosen to make a pair to sing the first song. Lovely. Total number of different pairs that can be chosen. That one is about as clear-cut as it sounds. I can have one of the men, so I've got 17 options, and I've got one of the women, so I've got 26 different options. They make their pair, 17 times 26, sorted. Now, 2 of the men are going to be chosen to make a pair to sing the second song. Ben thinks the number of different pairs is 136. Mark thinks blah, 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 372. Who's correct? Right. The best thing to do here is ignore what Ben thinks and what Mark thinks and do it for yourself. These sorts of questions, they're meant to kind of guide you towards the answer. Figure it out for yourself first. 2 of the men are chosen as a pair to sing the second song. So to begin with, I've got 17 choices. Then I've got 16 choices if I've already chosen one. And 17 times 16, that's going to give us 272. There's a reason I know that, and suddenly that makes Mark's option look very tempting. Now, question is, if I'd chosen, say, Jim and Phil as my singers, if I'd chosen Jim first and then Phil, does it matter if I'd have done it the other way around? Not at all. So in our list of all the possible options, I'll have Jim, then Phil, and somewhere down the line I'll have Phil, then Jim. And because that order doesn't matter, they're no longer unique, which means we need to divide by 2. So it's 136, the order doesn't matter, therefore Ben is correct. Always worth bearing that in mind. See you working out through. Think about your logic as best you can. Quickfire questions. In a rate of 8 people, gold and silver medal are awarded. Does the order matter? Absolutely. They're not going for the same reward, so this would just be 8 times 7. In a class of 30 students, I select 2 of them to give it attention to, because I'm not a nice person that way. Does the order matter? No, because these 2 people still have a detention. One doesn't have a super special detention, therefore divide by 2. The Queen has a head male corgi and she wants to breed. Lovely. She picks 2 amongst her 6 female corgis. How many selections can we make? She picks 2 of her 6 female corgis. So we know we're going to do 6 times 5 here. Do we need to divide by 2? Does the order matter? No, it doesn't. The order doesn't matter. Therefore, we want to divide by 2. A bag has 5 differently coloured counters. Pick any colours that you want. Alice picks 1. Bob's picks 1. How many possible selections are there? Does it matter which way out they get? Does it matter that red and green pop out? Yes, it does, because it could be red going to Alice, green going to Bob, or it could be the other way around. The order matters, therefore we don't divide by 2. You might be starting to see the pattern here. With that in mind, I believe actually there are a lot more questions going on. I'm assuming some of you might have hit quick pause already. What I will just do is reveal the answers for this and let you have a lovely look at those. Pause the video if you're interested, or if you want to see how the working out was done. Otherwise, here is exercise 2. As always, I'm going to make myself vanish for a bit, let you have a look at them and have a good go at them for yourself. Hello again, ladies and gents. Right, it's the final bit from me, and I can't resist these kinds of puzzles. As soon as I see the skull and bones, usually all my students are very keen to have a go at it and see what they can get. If anything, I've kind of got to drag them back and make sure that they have a go at the more basic ones to make sure that they've got the concepts. Nonetheless, even I can't resist having a go at these. So before we look at Frosty's answer, what I'm going to do is go through it with you at home. What you'll notice I've done here, I don't think it's anything too fanciful, I dare claim to begin with, is I've written all of the numbers, I had written all of the numbers between 1 and 20. I think that's a fair enough thing to start with, and I think it's also a nice, easy way to help you visualise what's going on. A very careful reading of the questions needed. I choose some numbers between 1 and 20. That's awful, to begin with, because that adds quite a lot of randomness into it that isn't particularly friendly. How many selections are there such that the range of the numbers in my selection is 6? I won't lie to you, I was sat there having a headache with this one for quite a while, partly because I forgot to include the range bit. I forgot to include the fact that we can have some numbers that may or may not be relevant at all. So let's break this down. Let's start with just a couple of numbers where we know that the range is 6. So in my case, I'm going to say, let's go with 9 and 15. It's very tempting to think, right, well, okay, so if I had 9, I could have 15, or 9, I could have 2, so surely I've got 2 choices there. You get bogged down very, very quickly with that. Let's have just to think about 9 and 15. What if I'd chosen 9 and 15? Again, Frosty points out that we've chosen some numbers. So let's say that 9 and 15 for now are fixed. Because the question is, how many ways are there of picking all the numbers in between? Because surely I could have them, or I couldn't have them. So what if I have 10, what if I don't have 10? Actually, that's quite nice, because for all these numbers in between, we can say exactly the same thing. Now, where anybody else would potentially get frustrated by that, where some of you will be sat there thinking, I could have 9, I could have 15, I could have 10, I could have 12, I could have... I'm going to skip there we go. I could have 10, I might not have 10. I might have 12, I might not have 12. I might have 13, I might have 13 and 14. I might not have 13 and 14. Where that gets quite tense for a lot of people, it's actually a mathematician's dream. Because we're saying the same thing about each number, which means that the same pattern is going on. So, let's assume for now, 9 and 15, they're fixed. 10, do we have 10? Don't we have 10? That's 2 options, right there. We either do or we don't have it. Does it change the range? No, because remember, if you know your statistics, range is highest, take away lowest. So it doesn't matter. So if 10's there, it doesn't change the range. It's still 15, take away 9, which is 6. What about 11? Same story. So we now have 2 options. 2 options whether or not we include 10, 2 options whether or not we include 11, and that plays out the same for all the numbers in the sequence. 2 options for 10, 11, 12, 13 and 14. What happens if my first set had been, let's go with 2 and add 6 to that, we get 8. So in this bracket on the left-hand side, I've got my range. If I've got 2 and I've got 8, I've got a range of 6. Does it matter about any of these numbers in the middle? Sort of, but it suffices to say we've got 2 options for 3, 2 options for 4, 5, 6 and 7. That right there is 2 to the power of 5, exactly the same as what we had before. So assuming that our first and last number are fixed, all of the numbers in between, we've got 2 to the power of 5 options, whether or not we include all of the numbers in between. So that begs the question, how many options do I have to begin with? There's a nice, easy way, I claim, of figuring that out. You'll notice that if I'd selected 1, then I must have my highest number as 7. That's fixed, that can't be changed. If I'd selected 2, my highest number must then be 9, and so on. How far can I extend that up to? Can I extend it up to 10, choosing that as my lowest possible number? Yes, I can, because 10 plus 6 is 16, so that's still a valid option. The question is, when does it stop? When does choosing my lowest number stop being a valid option? And I argue that it stops my minimum number, if you want, is 14. Because 14 we can add 6 to that to get 20. So there you go. I've got 14 different options for my minimum number. You could say, well, what if I went the other way? You're actually making a symmetric argument. You're saying, right, I've chosen my maximum as 20, and I can come right the way down to 7. So you're doing the same thing, but in reverse. So for our minimum number, we've got 14 options. And of that, whether we include the numbers in the middle, 2 to the power of 5. And if I were to do 14 times 2 to the power of 5, we would get an answer of 448. I claim. This is the really exciting bit. This is the bit where I think I'm pretty justified in what I've written. I don't think I've included anything that was out of the context. First off, does the answer match? Then we're going to look more interestingly at whether or not the reasoning matches. Yes! 448! That is a moment of relief, partly because I did do this in one take, other than ignoring the 1 to 20 number line, but I didn't want to bore you with that. Is the reasoning the same? It's always interesting if the reasoning is different, partly because we've gone through 2 very different methods to get the same answer. He starts supposing the smallest number was 1, the largest number would have to be 7. That's absolutely fine. Same start, talking about minimums. For the 5 numbers in between, he's gone for the same way. Each number may be chosen or not, so there's 2 possibilities, on or off. That's 2 to the 5. Okay, he called that 32. Fair enough. And okay. 14 choices for the smallest number from 1 to 14. So we've got 32 to the power of 5 times 14. Oh, there we go. So, other than writing it in pretty much a different way, I know I can't prove it to you. Would have been easy for me to reveal the answer, look at it, and just copy it out. But actually, I think that's brilliant. Same solution for different answers. I would like to point out, I've been in email contact with him quite a bit. Never actually met the man. Oh, well played, Frosty. You know what they say about great minds, folks. In my nerdy excitement, then I think that's a good way to leave it at that. So this is the second on 2 videos in counting. Like and subscribe if you enjoyed that. In future, I'm going to be moving on to what are known as bases and sets. I'll level with you, they aren't massively heavy on the GCSE spec. It is possible to get your GCSE without really knowing about sets and bases other than Venn diagrams. Otherwise, if you enjoyed it, click like and subscribe. I've been David Myers. Thanks a ton.